Good day, and welcome to the Big Weather Guy channel in a new series called Weatherwise. Here, I will attempt to shed a tiny bit of light on the hows and whys of what makes weather work and why I find it so fascinating. I'm going to do this through short, relatively non-technical bites at the apple of meteorology. There will be some elementary mathematics and physical concepts, but I will try to keep it pretty basic, and I truly hope you get something out of it. So buckle up. The first episode will dive into why it is that we even have weather on Earth. So, why do we have weather? Ultimately, it is because of the following three details. We have a nearby star, the sun, that blesses us with its heat and light. Also, we thankfully have an atmosphere on our planet, which is a blessing for those of us who enjoy breathing. And finally, it is because our planet is roughly spheroid shaped. And here I most humbly beg the pardon of our friends who hold on to the theory of the flat earth. So these three facts are ultimately at the very root of all of the complex mathematics and physics, the massive supercomputers, the need for tornado safe rooms and flood control dams, and the need for TV meteorologists who break into the latest episode of Survivor and occasionally have to take off their jackets, roll up their sleeves, and put on their serious faces. Now, point number one, this sun of ours, it shines on us. That is great. What does the sun actually provide? Well, in short, it provides us with energy in the form of radiation. Radiation, simply put, is the energy released across the electromagnetic spectrum. In this diagram here in the upper left, we see that the spectrum, starting with the shortest wavelength here, the left, being the gamma radiation. Gamma rays are released from high energy cosmic events like supernova explosions, pulsars, or on the Earth, they are released by such events as the natural radioactive decay of thorium or uranium, as well as man made events such as nuclear reactions in reactors or from nuclear weapons. The spectrum moves then into the X rays and then on to the ultraviolet rays or UV radiation. Next, here is the range of visible light, light detectable by our eyes. Lower down the energy ladder, it moves into the infrared radiation range, to microwaves, and eventually to radio waves, which are the longest wavelength and lowest energy categories. So that is the radiation spectrum. The energy that we receive from the sun is shown here, and it falls between about 200 nanometers and 2500 nanometers in wavelength. If you look at the graph in the lower right, within the range of 200 nanometers to 2500 nanometers, you can see about 5% of that energy from the sun is UV. 42% of that energy comes in as visible light, and the remaining 53% comes in as infrared energy or radiant heat energy. Now, the gray curve on this graph you see here is indicative of the total solar irradiance that reaches the top of the Earth's atmosphere from the sun. The red curve is the approximation of the irradiance that ultimately reaches the Earth's surface. As you can see, there's a significant amount of energy at different wavelengths that doesn't make it to the surface. These little notches right here. Take note of these distinct wavelength bands that show absorption of that incoming radiation. We will discuss this in more detail in a moment. At the top of the atmosphere, the irradiance is approximately 1360 watts per meter squared, and only about 1000 watts per meter squared makes it to the surface. So that encompasses the first of the three facts that ultimately drive weather, that the sun provides energy. For our second key point of why weather exists, that the Earth has an atmosphere. This diagram is a representation of what is called the Earth's energy budget, which demonstrates what happens when the solar energy that reaches the Earth interacts with the atmosphere. As you can see, about 30% of the incoming radiative energy is scattered back in the upper atmosphere, reflected by cloud cover, or reflected by the Earth's surface. 47% of the radiation is absorbed by the land and ocean, and the remainder is absorbed by the air and different chemical components present in the atmosphere, such as ozone, water vapor, dust, ash, and smoke. This is what those distinct bands of energy absorption that were shown in the previous slide, where energy at specific wavelengths interact with and are absorbed by the aforementioned components. As a quick aside, to discuss the importance of the balance of energy and the chemical makeup of the atmosphere, those of you who are Gen X like me and older will remember the concerns that surrounded the dissipation of the ozone layer. Ozone is a naturally occurring molecule of three bonded oxygen atoms, O3 by chemical name, and is very important in the absorption of ultraviolet energy from the sun before it can reach the surface. Starting in the 1970s, it was found through observations and research that the layer of ozone was being depleted by the release of various industrial chemicals related to refrigeration and propellants, such as halocarbons and chlorofluorocarbon chemicals. These chemicals, when released in the atmosphere, eventually made it up to the level where atmospheric ozone is concentrated. Once there, in the presence of solar energy, it interacts with the ozone and catalyzes with the O3 and causes it to break up into an oxygen atom and gaseous oxygen molecule, O2. The net impact of that was that highly energetic UV radiation that used to be absorbed by ozone was no longer being absorbed. It was making it to the surface. UV radiation is a very real culprit in many adverse conditions, including skin cancer and cataracts. In 1987, through the signing of the Montreal Protocol, the most destructive of the chemicals were outlawed internationally, and by the early 2000s, ozone levels had begun to recover. NASA currently projects that the ozone hole over Antarctica could be fully healed in about the next 40 years. Okay, well, back to the diagram here. The solar radiation that is absorbed at the surface by the land, the trees, houses, water, humans, etc., does not just stay absorbed, though it probably feels like it in August. Ultimately, this energy is re-emitted as radiation back out into the atmosphere in what is known as long-wave radiation, latent heat, and conduction. Those emissions stream out from the Earth back into space and play an important role in maintaining the balance of heating and cooling of the planetary system as a whole. The details of the physics and chemistry of atmospheric radiation could rightfully consume an entire year's worth of lectures, but we are just wanting to hit on the very highest of high levels of this concept that answers that second fact, that the Earth's atmosphere plays a vital role in the energy balance of the Earth. Here is an image that you all no doubt remember from a grade school Earth science or geography class. This concept of the tilt of the Earth on its axis and the precession of the planet around the Sun during the course of the year, and it starts to lay the groundwork for establishing the third elementary fact of what drives weather, namely, that the Earth is round. In the northern hemisphere, during what is our summer months, the tilt of the North Pole is towards the Sun, which is why we have longer days. Not only are we getting longer exposure to the Sun's energy each day, but most importantly, the Sun is higher in the sky, and the angle of incoming energy is closer to perpendicular to the surface. It is just the opposite for the northern hemisphere in our winter, as is shown on the left-hand side of the diagram. With the North Pole tilted away from the Sun, like here on the left, the time that the Sun is above the horizon is not only dramatically shorter, but the incoming energy is hitting at a much more shallow angle. To examine this in a bit more detail, let's look at this slide. In the upper left, you can see the representation of what is going on in terms of solar angle. At a low latitude, closer to the equator, sun angle is closer to 90 degrees, with 90 degrees being directly overhead at noon. I want you to imagine a thought experiment. Imagine that the sun is a heat lamp and it shines a 1000 watt beam of energy that is exactly a square that is 1 meter per side. If this is directly overhead of your location at noon, the 1000 watts of energy are shining on and heating up a square meter of surface only. So that patch is getting 1000 watts per square meter. This is what it would be like at the equator. Now, if you're up here in the mid latitudes like us, the sun is not directly overhead at noon, but the energy is impacting the surface at an angle. As a result, that 1 square meter of energy coming out of the lamp is spread out over a larger surface area. For the sake of argument, let's say that that area illuminated on the ground is now 3 square meters. As a result, that 1000 watts from the lamp are now trying to heat an area 3 times as big as the same lamp at the equator. So the amount of energy is only 1/3 as much per square meter, 333 watts per square meter, as compared to 1000 watts per square meter, the equator. We are getting close to tying off all of these concepts into a unified argument. We have energy coming from the sun into our atmosphere, interacting with clouds, various surfaces, water, land, etc., different regional atmospheric chemistries, and all of that. And you have the Earth radiating long wave radiation back out into space. You have all of that occurring at widely ranging angles of incidence, resulting in wide ranging amounts of energy, depending upon where you are on the Earth. All of that is tied into a giant interconnected fluid system. That is the big key. Now, there is a dictum in nature that nature abhors a vacuum. In short, nature doesn't like it if there's too much of something in one location and not enough of that same thing in a nearby location. Just as water will spread out to find its level, the same thing applies to energy in the atmosphere and ultimately the air in that atmosphere. If you examine the map in the upper left, this is the data of the balance of incoming radiation minus the outgoing long wave radiation across the globe in March on average. Warm colors show regions where the Earth does not radiate enough long wave to offset the incoming solar radiation. Cool colors are the opposite, where the Earth is radiating more long wave out than the incoming solar energy coming in. So, that data is demonstrated there in the graph on the bottom right. That shows the abundance of net radiation in the low latitudes around the equator here, and the deficit of net radiation at the high latitudes towards the north and south poles. Taking into account all of that, which we've discussed in the last several slides, we'll reach our last real substantive slide of this lecture. We're not going to go into it in very much detail, but I just want to sort of tie everything together. We have a large interconnected fluid system with wide-ranging disparities in energy and a physical dictum that that system should attempt to equalize these disparities, i.e., for nature to fill the vacuum that it dislikes. So what is going to happen? In short, weather. The air in the regions of net positive energy is going to try to fix the air in the regions of net negative energy. And when that happens, you have transport of air, movement of air, mixing of air, you have weather. You have the full planetary system trying to balance the system's overall energy budget to even everything out to zero. All of that brings us to the summary point that we need to remember from this lecture. Weather, from its most beautiful and benign forms to its most violent and dynamic forms, is ultimately a result of the atmosphere attempting to balance out the variations in energy present within the system and moving air around to try to accomplish that. Now, obviously, that is a fairly bold, grand statement, and there are so many more details, but in its most elemental form, that is what weather is. In the next lessons, we will dig more into details of the how and why of that. With that, I will conclude this first lesson of Weatherwise. I hope that you've enjoyed this, and if you are so inclined, I encourage you to consider hitting the subscribe button so that you don't miss future episodes, as well as the other parts of the channel that will be coming out, such as discussions about significant upcoming weather events as we come into the storm season. Thanks for watching, and I will see you next time when we will dive into the ideal gas law and how it drives a major portion of the weather system, namely atmospheric pressure. See you then. Cheers.